talk about the algebra of functions, sums, difference, products, and quotients. We can now use subtraction, addition, multiplication, and division to combine different functions and obtain new ones. For example, let's say that f of x is simply x plus 2, and g of x is x squared plus 1. Well, we can look at, let's go down here to these generalized formulas. If I want to say what's f plus g of x, it's simply f of x plus g of x. So for example, f of x, it's x plus 2. Bring your plus symbol over. G of x is x squared plus 1. Combine like terms, x squared plus x plus 3. And that would be your f plus g of x. We're going to have some examples here in just a moment going over these ideas. One thing to remember is that if you have f divided by g of x, f of x divided by g of x, the rule is that g of x cannot be 0. Why can't g of x be 0? You cannot divide by 0, and so that's why we have to have that stipulation. The domains of the the domain of the algebra of functions is simply the domain of the intersections of each. For example, f plus g of x, the domain of f plus g, and the domain of f minus g and f times g are again the intersections of the domains of f and g. The domain of the division is also the intersection, except you have to it's also the intersection, except you also have to include where you cannot have the denominator g of x be 0. Let's look at a couple of these examples. Here we want to find each of the following. So here we go. We have f of x is x plus 1. We have g of x is the square root of x. So first I'd like to find f plus g of x. So I have f of x, bring your addition symbol down, and then g of x. Nothing can be combined, nothing is like, so we leave it as it is. What if I want f plus g of 6? Well, what's f of 6? Well, let's do a side note and figure that out. F of 6 is simply evaluating. I plug in 6 wherever I see an x in my f of x. So I have 6 plus 1, or 7. Well, what's g of 6? Again, it's evaluate. So wherever I see an x, I'll plug in a 6. And so now I can say, oh, okay, well, f of 6, I got 7. Bring your plus symbol down. G of 6, I got 3. Combine them, you get 10. What if I wanted f plus g of negative 4? Well, that's f of 4 of negative 4 plus g of negative 4. So let's again do our little side note. F of negative 4, simply evaluating, plugging in. Negative 4 plus 1 gets me a negative 3. And let's find g of negative 4. Again, that's a simple evaluate. So in our g function, we'll plug in negative 4. So I get the root, square root, negative 4 plus 3, which will give you the root of negative 1. The square root of negative 1 is, by definition, I. Now I, this idea is imaginary numbers, which is complex realm. Complex number realm. So this idea here, for this class's purposes, D and E does not exist. So, for example, the number negative 4 is not in the domain of the g function. Why? Because I got out something that is imaginary, is complex. So let's write ourselves a note here. If I get f of negative 4 is negative 3 plus something that does not exist, then the whole thing does not exist. I can't do this one. So let's talk about this. Note, negative 4 is not in the domain of g of x. Therefore, it is not in the domain of f plus g of x. And therefore, this problem, this answer, does not exist. Let's talk about the domain of f plus g of x. Remember, the idea is that the domain of f plus g of x will be the idea of the intersection of where both of these functions' domains are. The domain of f, the domain of g, the domain of, any of the algebra will be the intersection of these two domains, with the exception of this one being where g of x cannot be 0. That has the addition there. Addition of that, okay? So let's figure out, well, what is the domain of f plus g of x? Well, we got f plus g of x to simply be this function, right? But remember, it's simply the intersection. The domain of f of x, where f of x is x plus 1, the domain of this is all real numbers. Why? Because there's no variable in the denominator and there's no even indexed root, therefore it's all real. The domain of g of x needs some work. The domain of g of x, we will see that it's negative 3 to infinity, and here's why. When you ask yourselves your two questions, do I have a variable in my denominator? No, for g of x. Remember, g of x was the root of x plus 3. Question 2, do I have any even indexed roots? Well, yes, you do. You have an even indexed root right here. When you say yes to this, what are you supposed to do? You're supposed to take the root, set it greater than or equal to 0, and solve. So if I take what I have in my root, and I solve this, square both sides, okay, finish this up, draw a number line. Remember, we talked about these in earlier lectures. Draw a number line and put your value here. Greater than or equal means closed circle. Closed circle means bracket, okay? And this inequality is saying to shade to the right. So I'm going to go from negative 3 all the way out to infinity, which is what we have here, negative 3 all the way out to infinity. Now, we had to talk about what is the domain of f plus g. Well, the domain of f plus g is where they are both defined. F of x is defined everywhere, and g of x has a stipulation, which means that they are both defined at the stipulation. Okay? Let's look at some more examples. We'll look at composite functions. Composite functions are functions that depend on some input in and of itself that is an output of another function. To write this, and keep in mind, this is f composed of g. That's how we say that, f composed of g. The way we can rewrite this to understand this a little better is f of g of x. F of g of x. Where x is in the domain of g, and g of x is in the domain of x, of f. Let's see if we can figure these out. Here I have my f of x function, I have my g of x function. And I would like to find the following. So I want to rewrite this. F of g of x. That's f of g of x. Well, what's g of x? X squared minus 3x plus 8. Oh, well, what's f of this value? It's an evaluate. Wherever I see an x in my f of x, I'll simply replace it. Right? Wherever I see an x in my f of x, I'll simply replace it with all of this. Okay, so I have 2 times x, so that's all of this, plus 5. Distribute. 2 times x squared, 2 times a negative 3x, 2 times 8, plus 5. Finish out the problem by simply combining like terms. We've got the 16 and the 5 are like. Finishing out the problem, 2x squared minus 6x plus 21. Let's work another one. G composed of f of x. That's g of f of x. G of f of x. Well, what's f of x? So we say that's g of. Well, what's f of x? 2x plus 5. Oh, that's a simple evaluate again. Wherever I see an x in my g function, I'm going to put 2x plus 5. So I have x squared, or 2x plus 5 squared, minus 3 times x, or 2x plus 5, plus 8. Again, this is evaluating. 2x squared plus 5 is you've got 2x squared, or 4x squared. You've got 2 times 5x twice, and you've got 5 squared. What I did was I did 2x plus 5 twice. 2x times 2x, 4x squared. 2x times 5 is 10x. 2x times 5 again is 10x. 10x and 10x is 20x. And 5 and 5 is 25. Distributing this second part, negative 3 times 2x, negative 6x, negative 3 times 5, negative 15, add the 8. Simply combine your like terms. I have 4x squared. 20x is like with negative 6x, which will get you 14x. 25 is like with negative 15 and positive 8. Combining those, we get 18. Okay, let's do another one. This time, let's find f of g of 7. Well, that's f of g of 7. Well, I don't know what g of 7 is. Let's figure that out. Let's make a side note. G of 7. In my function here, I'm going to replace the x's with 7's. 7 squared minus 3 times 7 plus 8. Well, that'll be 49 minus 21 plus 8. Well, that'll get you 36. So I want f of g of 7, which is 36. So I want f of 36. If I want evaluate, wherever I see an x, I'll now put a 36. So I have 2 times 36 plus 5, or 77. Okay, let's do one more. Let's look at g of f of 7. So that's g of f of 7. Well, I don't know what f of 7 is, so let's do a side note and figure that out. Again, we're going to evaluate simply plugging 7 in where I see my x's here in my f function. So I have 2 times 7 plus 5, well that's 19. So g of f of 7, so that's g of 19. Evaluating in my g function, wherever I see an x, I put a 19. So 19 squared, 631, 3 times 19, 57, plus 8. Running out of room here, we get 312. Very good. Okay. Let's look at a couple more examples. We want to find the following. F of g of x. So that's f of g of x. G of x is x minus 3. This is an evaluate where I'm going to replace my x in my f function with x minus 3. So I have the root of x minus 3. Let's find g of f of x. Again, so it's g of f of x. So g of root of x. So wherever I see an x in my g function, I'll put root of x. So I have square root x minus 3 on the outside. We want to find the domains of both of these functions. We want to find the domain of f of g of x, and we want to find the domain of g of f of x. Okay. In this is f of g of x. If I want to find the domain of it, I can simply talk about this function. Question 1. Do I have a variable in my denominator? No, I don't even have a denominator. Question 2. Do I have any even indexed roots? Yes. What are we supposed to do when we have even indexed roots? We're supposed to take our roots, set it greater than or equal to 0, and solve. So I'm going to take my items just in the root. I'm going to square both sides to get rid of that root. Simplify. Here is my domain. So I can say that it's the set of all x such that x is greater than or equal to 3. In interval notation, right, I can draw myself a number line. I can put that number on it. Greater than or equal means solid circle. Greater than means shade to the right. So I can see that this is a bracket on the 3. Scroll out to infinity, parenthesis. For the domain of g of f of x, this is your g of f of x. Then we're going to ask ourselves the 2 questions. Do I have a variable in my denominator? No, I don't have a denominator. Question 2, do I have any even indexed roots? Yes. Where is my root? It's just right here. So I'm supposed to take my root, set it greater than or equal to 0. It does not matter what's on the outside of your root, simply talk about the root. I'm going to square both sides to get x greater than or equal to 0. So this is my domain. It's the set of all x such that x is greater than or equal to 0. Again, we can put this into interval notation. Draw our number lines, put our value here. Greater than or equal means solid circle, bracket. The greater than means shade to the right. So now I have my interval notation, bracket, 0, all the way out to infinity, parenthesis. Okay. Let's do one more example. We want to work with f of g of x, that's f of g of x. F of x over 5. Okay. So that's going to mean that everywhere in my f function where I have an x, I replace it with x with 5 over x. So I have 1 over 5 over x minus 2. We have to simplify this. We have common denominators, right? We'll simplify. Common denominators will simplify, and then fraction division, flip this over. Okay, again, let me write you a note here in case you don't remember. This idea needs a common denominator. 5 over x minus 2 over 1, common denominator between 1 and x is an x. So if I have 2x, that's 2 times x over x. Now, they have the same denominator, put them over the same denominator, and then take numerator, middle, numerator. Fraction division is you multiply by the reciprocal, so we're flipping here. This is 1 times the flip of this, 1 times the flip of that, which would just be this. Okay, very good. Let's work with the next one. We want to look at g of f of x. That's g of f of x. So g of 1 over x minus 2. So wherever I have an x in my g function, I'm going to replace it with this. So I have 5 over 1 over x minus 2. Again, fraction division becomes fraction multiplication, which will give you 5x minus 10. We want to talk about the domains of f composed of g and g composed of f. This is your f composed of g function. This is your g composed of f function. If I want to talk about the domains of f composed of g, you ask yourself two questions. Do I have a variable in my denominator? Yes. Do I have an even index roots? No. But I do have a variable in my denominator. How am I supposed to answer this when I have a variable in my denominator? Well, you're supposed to take your denominator, set it equal to 0, and solve. The values that you get will be out of your domain. So my domain here is the set of all x such that x cannot be 5 halves. Everything else is perfectly fine to have, but you can't have 5 halves here. If I want to talk about the domain of g composed of f, is there a variable in my denominator? No, I don't have a denominator. Are there even any even indexed roots? No. If I answer no to both, then my domain is all real numbers. Or negative infinity to positive infinity. If I want to go back, I'm sorry, this is set notation. If I want to go back and do interval notation, we have our extremes with our 5 halves. Everything is fine except for the 5 halves. So we can say negative infinity to 5 halves parentheses means don't include. Jump over the 5 halves and continue on to infinity.